Before the 20th century, physics appeared to be standing on solid, almost unshakable ground. For more than 2 centuries, the laws discovered by Newton had explained motion with astonishing accuracy. Planets moved exactly as predicted, cannons fired along precise arcs, pendulums swung with clockwork reliability. Nature seemed to obey clear, deterministic rules. If you knew the forces and starting conditions, you could calculate the future with confidence. This success created a deep belief that the universe was fundamentally continuous, smooth, and predictable. By the late 19th century, this confidence had only grown stronger. James Clerk Maxwell had unified electricity, magnetism, and light into a single elegant theory. His equations showed that light itself was an electromagnetic wave, oscillating smoothly through space. These waves could have any wavelength, any energy, and any frequency. Nothing in the equations suggested limits. The universe, according to classical physics, was an unbroken continuum. Many leading scientists believed that physics was nearly complete. Famous figures openly stated that future research would focus only on refining measurements, adding decimal places to known constants. The big ideas, they thought, were already discovered, but this belief rested on an assumption that nature always behaved continuously and that energy could be divided without end. Quietly, experiments began to challenge this assumption. One of the most troubling issues arose from the study of heat and light. When objects are heated, they glow. A piece of iron in a fire first turns red, then orange, then white as the temperature increases. Physicists wanted to understand the exact relationship between temperature and the light emitted. To study this, they used an idealized object known as a blackbody, a perfect absorber and emitter of radiation. Experiments showed a very specific pattern. At lower temperatures, blackbodies emitted mostly long, wavelength radiation. As temperature increased, the peak of emission shifted toward shorter wavelengths. But crucially, the intensity of radiation did not increase endlessly at short wavelengths. There was a clear cutoff. The energy output dropped off sharply in the ultraviolet region. Classical physics could not explain this behavior. When physicists applied known laws to blackbody radiation, the mathematics led to a catastrophic prediction. According to classical theory, the energy emitted at short wavelengths should increase without bound. The equations suggested that a hot object should release infinite energy in the ultraviolet region. This absurd result became known as the ultraviolet catastrophe. It was not a minor discrepancy. It was a complete failure. The equations worked beautifully at long wavelengths, but collapsed entirely at short ones. Nature was clearly imposing a limit that classical physics could not justify. At first, scientists hoped the problem could be solved with better approximations or more refined models of matter. Some tried modifying assumptions about atomic vibrations. Others attempted to adjust boundary conditions. But no matter how the equations were rearranged, the catastrophe remained. The mathematics itself was broken. This was deeply unsettling. Classical physics was built on the idea that energy flows smoothly, like water in a river. If an object could emit energy, it should be able to emit arbitrarily small amounts. There was no reason for emission to suddenly stop or weaken at high frequencies. Yet experiments showed exactly that behavior. The crisis was not limited to blackbody radiation. Other experiments were also producing uncomfortable results. The specific heat of solids, which measures how much energy a material absorbs as it warms, behaved strangely at low temperatures. Classical theory predicted a constant value, but real materials deviated sharply from this prediction. Again, The equations failed where experiments spoke clearly. Even the stability of atoms posed a problem. According to classical electromagnetism, electrons orbiting a nucleus should continuously radiate energy. As they lost energy, they should spiral inward and collapse into the nucleus. This would happen incredibly fast, in fractions of a second. Yet atoms were stable, matter existed. Classical physics offered no explanation. These failures pointed to a deeper issue. The assumption of continuity, once the greatest strength of classical physics, was becoming its weakness. The equations assumed that physical quantities could change smoothly and infinitely, but nature seemed to disagree. Despite these signs, many physicists resisted radical change. The success of classical theory had created intellectual inertia. It was hard to accept that the foundations might be wrong. Some believed the discrepancies were experimental errors. Others hoped new classical models would eventually fix the problems. Max Planck was one of the scientists drawn into this crisis, though reluctantly. He was deeply committed to classical physics and believed strongly in absolute laws of nature. He did not see himself as a revolutionary. When he began studying blackbody radiation, his goal was not to overthrow existing theory, but to preserve it. Planck approached the problem with mathematical discipline. He tried to derive an equation that matched experimental data exactly. Initially, he used known classical methods and statistical mechanics. These attempts failed. The ultraviolet catastrophe refused to disappear. Eventually, Planck made a move he later described as an act of desperation. Instead of assuming energy could vary continuously, he assumed that energy exchange between matter and radiation occurred in discrete amounts. These amounts were proportional to the frequency of the radiation. This assumption was completely alien to classical thinking. It violated the idea of smooth energy flow. It introduced a smallest unit, a grain of action that could not be subdivided. To make the mathematics work, Planck introduced a new constant, a proportionality factor linking energy and frequency. The equation worked perfectly, but at the moment of its introduction, the full meaning of this step was not understood. Planck himself viewed quantization as a formal trick, not a literal description of reality. He believed that continuity would eventually be restored at a deeper level. Yet the crisis of classical physics had already crossed a point of no return. The failure of classical physics before Planck was not just technical. It was philosophical. Classical theory assumed that nature was infinitely divisible, fully deterministic, and fundamentally predictable. The experimental evidence suggested otherwise. Limits existed where none were expected. Discreteness appeared where continuity was assumed. The ultraviolet catastrophe became a symbol of this breakdown. It showed that even the most trusted equations could lead to nonsense when pushed too far. It revealed that physical intuition, shaped by everyday experience, was unreliable at microscopic scales. This crisis forced physicists to confront an uncomfortable truth. The universe did not have to obey human expectations of smoothness and simplicity. Nature could be granular, restricted, and fundamentally strange. Planck's work emerged directly from this failure. Without the collapse of classical explanations, there would have been no reason to question continuity. Without the stubborn refusal of experiments to match theory, no one would have dared to introduce quantized energy. The classical physics crisis was not a sudden collapse, but a slow accumulation of contradictions. Each failure chipped away at confidence. Each unexplained result widened the gap between equations and reality. By the time Planck introduced his constant, the old framework was already cracking. What followed would become quantum theory, but its roots lie in this period of confusion and doubt. The old universe, governed by smooth curves and infinite divisibility, was giving way to something radically different. The crisis before Planck was the moment when physics discovered that its most basic assumptions were wrong, and from that failure, a new understanding of the universe was about to be born. At the turn of the 20th century, physics stood at a crossroads without realizing it. The equations were elegant, the experiments were precise, and yet something essential was missing. The universe was producing answers that theory could not justify. Into this uneasy moment stepped Max Planck, not as a revolutionary, but as a reluctant problem solver driven by mathematical honesty rather than philosophical ambition. Planck was deeply rooted in classical tradition. He believed in absolute physical laws and was uncomfortable with probabilistic thinking. To him, nature followed strict rules that existed independently of human observation. This world shaped his approach to the radiation problem. He did not seek to invent a new physics. He wanted to rescue the old one. The challenge he faced was specific but profound. Experimentalists had carefully measured the spectrum of radiation emitted by heated objects. The data were precise and consistent. No matter what material was used, the shape of the radiation curve depended only on temperature. This universality fascinated Planck. It suggested a deep, underlying law of nature waiting to be uncovered. Existing theoretical formulas could partially explain the data. At long wavelengths, classical predictions matched experiments well. At short wavelengths, they failed catastrophically. Planck tried to stitch together known results, hoping to derive a single expression that worked across the entire spectrum. Every attempt collapsed under mathematical scrutiny. Time was running out. The discrepancy was becoming impossible to ignore. Experimental evidence was overwhelming, and the theoretical gap was embarrassing for physics as a whole. Planck realized that no amount of refinement within existing assumptions would solve the problem. Something fundamental had to change. The change came not from intuition, but from calculation. Planck turned to statistical mechanics, a framework developed by Boltzmann, which related microscopic states to macroscopic properties. This approach already made him uneasy because it introduced probability into physics. Nevertheless, he used it as a mathematical tool. To make the equations fit the data, he made a radical assumption. The oscillators responsible for emitting radiation could not possess arbitrary energies. Instead, their energies were restricted to discrete values. This was not a philosophical statement. It was a mathematical one. Planck assumed that energy could only be exchanged in multiples of a basic unit proportional to the frequency of radiation. The proportionality factor was a new constant, later named after him. With this assumption, everything clicked into place. The derived formula matched experimental data perfectly at all wavelengths. The ultraviolet catastrophe vanished. The radiation curve emerged naturally from the mathematics. For the first time, theory and experiment were in complete agreement. Planck presented his results in December 1900. The announcement was quiet, almost understated. There was no dramatic declaration of a new world view. He introduced the constant as a fitting parameter, not as a fundamental feature of reality. Even then, he hoped that deeper classical reasoning would someday eliminate the need for quantization. But the constant refused to disappear. The new number had a strange character. It was incredibly small, yet it carried profound implications. It had dimensions of energy multiplied by time, a quantity later known as action. This suggested that action itself might be quantized, not just energy. The implication was subtle but devastating to classical assumptions. For centuries, physics had assumed that processes could be divided indefinitely. Motion could be broken into smaller intervals, energy into smaller amounts, time into finer slices. Planck's constant suggested a limit. Below a certain scale, division lost meaning. Nature operated in steps. At first, the physics community largely ignored the deeper meaning of this idea. Many saw Planck's assumption as an artificial trick, useful but not physically real. After all, nothing in everyday experience hinted at quantization. The world appeared smooth and continuous. How could such discreteness be fundamental? The answer lay in the size of the constant itself. Planck's constant was so small that its effects were invisible at macroscopic scales. Only when dealing with atoms and radiation did its influence become apparent. This explained why classical physics worked so well for large objects while failing at microscopic ones. Slowly, the significance of Planck's constant began to sink in. It was not just a parameter in one equation. It defined a scale at which classical ideas broke down. It marked the boundary between two regimes of reality. Above this scale, continuity was a good approximation. Below it, the universe behaved differently. The constant also introduced a new way of thinking about physical laws. Instead of smooth trajectories and deterministic outcomes, it hinted at restrictions and thresholds. Processes could occur only if sufficient energy was available in discrete amounts. This idea was profoundly counterintuitive. Einstein was among the first to grasp the seriousness of Planck's assumption. In 1905, he applied the concept of quantized energy to light itself, proposing that electromagnetic radiation consisted of particles later called photons. He used Planck's constant to explain why light could eject electrons from metal surfaces only above certain frequencies. This explanation went far beyond Planck's original intent. It suggested that quantization was not just a property of matter interacting with radiation, but a property of radiation itself. Light, once the ultimate symbol of continuity, was now discrete. With each successful application, Planck's constant became more deeply embedded in physics. It appeared in equations describing atomic structure, chemical bonding, and thermal behavior. It governed how electrons occupied specific energy levels rather than arbitrary ones. It explained why atoms emitted light at specific frequencies instead of continuous spectra. The constant also redefined what physicists meant by measurement. Because it linked energy and frequency, it implied that certain pairs of physical quantities could not be known simultaneously with unlimited precision. This idea would later be formalized as the uncertainty principle, where Planck's constant set the lower bound of uncertainty. What began as a desperate assumption became a cornerstone of modern science. The constant that Planck introduced reluctantly became unavoidable. It was woven into every successful theory of microscopic phenomena. Perhaps the most remarkable aspect of the birth of Planck's constant is that it emerged from failure, not success. It was born from the inability of classical physics to explain reality. It was not predicted by philosophy or intuition. It was forced into existence by experimental facts. Planck himself took years to fully accept the implications of his own work. He watched as younger physicists pushed the idea further, often in directions that made him uncomfortable. Yet even he eventually recognized that the constant represented something real, something fundamental. The birth of Planck's constant marked the moment when physics quietly abandoned the dream of a fully continuous universe. Without fanfare or revolution, a single number entered the equations and changed their meaning forever. It told the universe how small could be. It imposed limits where none were expected. In hindsight, this moment stands as one of the most important in the history of science, not because it provided an immediate new picture of reality, but because it opened a door that could never be closed. Once quantization was admitted, classical certainty was lost. The universe revealed itself not as a smooth machine, but as a structure built from indivisible steps. And at the heart of that revelation was a constant, quietly written into an equation, that forever altered humanity's understanding of nature. The idea that the universe might be continuous had been deeply ingrained in human thought for centuries. From the smooth motion of planets across the sky to the steady flow of time itself, everything about everyday experience suggested continuity. Classical physics reinforced this belief. Equations described curves without breaks, energies without smallest units, and changes that could be divided endlessly. The success of these ideas made them feel not just useful, but true. Planck's constant quietly dismantled that assumption. When energy was introduced as something that came in discrete packets, it was not merely a technical adjustment. It was a declaration that continuity, at least at the most fundamental level, was an approximation. Quantization meant that certain physical quantities could only take specific values. There were allowed steps and forbidden gaps. Nature was no longer a smooth ramp, but a staircase. This realization did not immediately reshape physics. At first, it was treated as a strange exception, limited to blackbody radiation. But as experiments accumulated, it became clear that quantization was not isolated. It appeared everywhere matter and energy interacted at small scales. The death of continuity was not metaphorical. It was literal. One of the first places this became undeniable was in atomic spectra. When atoms were heated or electrified, they emitted light at very specific wavelengths. These spectral lines were sharp and discrete, like fingerprints. Classical physics predicted a continuous range of emitted frequencies. There was no reason for atoms to prefer one color over another, yet nature insisted on selectivity. Quantization provided the missing explanation. Electrons in atoms were not free to orbit at arbitrary distances or energies. They occupied specific energy levels. Transitions between these levels released or absorbed energy in precise amounts. The emitted light reflected these discrete jumps. The spectral lines were direct evidence that continuity had failed. This idea reached a turning point with the model of the hydrogen atom. When quantized energy levels were introduced, the observed spectral lines emerged naturally from the equations. What had once been mysterious patterns became logical consequences of allowed and forbidden states. The atom was no longer a miniature solar system. It was a quantized structure governed by strict rules. The implications extended far beyond atomic physics. Quantization reshaped the concept of motion itself. In classical mechanics, particles follow precise trajectories. At any moment, their position and velocity can, in principle, be known exactly. Quantum theory replaced this picture with probabilities. Instead of definite paths, particles were described by wave, like distributions. This shift was deeply unsettling. It suggested that the universe did not merely hide information from us, but that such information did not exist in a definite form until measured. Continuity was not just broken, determinism was weakened. The idea that the future could be calculated exactly from the present began to crumble. Planck's constant played a central role in this transformation. It set the scale at which quantum effects became significant. When actions were large compared to this constant, classical behavior emerged as an approximation. When they were comparable, quantization dominated. This explained why the macroscopic world felt continuous while the microscopic world did not. The death of continuity also affected how energy flowed. In classical theory, systems could exchange arbitrarily small amounts of energy. In the quantum world, exchanges occurred in jumps. This introduced thresholds. Some processes simply could not happen unless sufficient energy was available. This explained why certain chemical reactions required minimum activation energies, and why light of too low a frequency could not trigger specific effects. Perhaps the most profound consequence of quantization was the uncertainty principle. By linking position and momentum through Planck's constant, it imposed a fundamental limit on knowledge. The more precisely one quantity was known, the less precisely the other could be determined. This was not due to experimental imperfections. It was a property of nature itself. This principle shattered the classical ideal of perfect measurement. It suggested that at the deepest level, reality was not composed of sharply defined objects with exact properties. Instead, it consisted of probabilities constrained by quantized limits. Continuity was replaced by a statistical structure. The impact of this shift reached into philosophy as much as physics. The idea that the universe operated on discrete rules challenged long-held beliefs about causality and reality. Events were no longer strictly determined, they were governed by likelihoods. This forced a reconsideration of what it meant to explain something scientifically. Quantization also revealed that stability itself depended on discreteness. Without quantized energy levels, atoms would be unstable. Electrons would spiral into nuclei, and matter as we know it would not exist. Continuity, once thought to guarantee stability, would actually destroy it. Discreteness was not a flaw of nature, it was a requirement for structure. As quantum theory matured, quantization extended beyond energy. Angular momentum, spin, and other physical quantities were found to be quantized as well. These properties did not vary smoothly, but came in fixed units. The universe appeared increasingly digital at its core. Despite its counterintuitive nature, quantization proved extraordinarily successful. Every experimental test confirmed its predictions. Technologies built on quantum principles transformed society. Lasers, transistors, and modern electronics all relied on discrete energy levels and quantum transitions. The death of continuity was not just theoretical, it reshaped the world. What made this transition especially striking was how quiet it was. There was no single experiment that announced the end of classical continuity. Instead, it faded away under the weight of evidence. One by one, classical explanations failed and quantized ones succeeded. Planck's constant stood at the center of this transformation. It was the numerical signature of discreteness. It told physicists how coarse the universe truly was at its smallest scales. It defined the granularity of reality. In accepting quantization, physics accepted that intuition based on everyday experience could no longer be trusted. The microscopic world obeyed rules that felt alien, even paradoxical. Yet those rules were consistent, testable, and deeply woven into the fabric of nature. The death of continuity did not mean chaos. It revealed a new kind of order, one built from limits and steps rather than smooth flows. In place of infinite divisibility came structure. In place of certainty came probability. And in place of classical simplicity came a deeper, stranger understanding of the universe. What began as a mathematical adjustment evolved into a philosophical revolution. The assumption that nature was continuous quietly died, replaced by a universe that moves in quanta, obeys limits, and reveals itself only in discrete glimpses. What made Planck's constant extraordinary was not just that it solved a theoretical problem, but that it revealed how deeply structure is embedded in reality. The number itself is almost unimaginably small, yet its influence is universal. It does not describe a particular particle or force. It defines a scale. It tells the universe how finely it can be divided, and beyond that scale, it refuses to cooperate with classical expectations. To understand how a tiny number could reshape reality, it is necessary to recognize what physics is really about. Physics does not merely describe objects, it describes limits. The speed of light limits how fast information can travel. Absolute zero limits how cold matter can become. Planck's constant limits how small actions in nature can be. It is a boundary written into existence. Before its introduction, there was no known lower bound to physical processes. Energy could, in principle, be transferred in arbitrarily small amounts. Motion could be subdivided endlessly. Measurement could be refined without limit. Planck's constant shattered that idea. It introduced a smallest meaningful unit of action, below which the concept of division loses physical meaning. This had immediate consequences for matter itself. Atoms are not miniature versions of the macroscopic world. They do not obey the same rules scaled down. The presence of Planck's constant ensures that electrons cannot simply fall into the nucleus. Instead, they occupy stable energy levels. These levels are not chosen arbitrarily. They are dictated by the value of the constant. If Planck's constant were even slightly different, the universe would look nothing like it does. If it were larger, quantum effects would dominate at everyday scales. Objects would behave unpredictably. Chemistry, as we know, it would not exist. If it were smaller, atoms might become unstable, and complex structures might never form. The fact that this number has the value it does allows stars, planets, and life to exist. In this sense, Planck's constant is a tuning knob of reality. It sets the balance between classical behavior and quantum behavior. It determines when the universe appears smooth and when it reveals its graininess. This balance is what makes the macroscopic world stable, while allowing the microscopic world to be dynamic and rich. The constant also redefined the relationship between observation and reality. In classical physics, measurement was passive. Observers revealed properties that already existed. In the quantum world shaped by Planck's constant, measurement becomes active. The act of observing influences the outcome. This is not due to technological limitations, but because interaction at small scales cannot occur without exchanging quanta of action. Every measurement requires energy. Every interaction requires a minimum disturbance. Planck's constant sets the scale of that disturbance. This means that at the deepest level, reality cannot be separated from interaction. Objects do not possess all properties independently of observation. Some properties emerge only through interaction. This insight transformed the meaning of objectivity. Physics no longer described a detached universe unfolding independently of observers. It described relationships, probabilities, and interactions constrained by fundamental limits. Reality became contextual. The influence of Planck's constant extended into time itself. In quantum theory, processes are not continuous flows, but sequences of allowed transitions. Time evolution occurs through changes constrained by quantized action. This does not mean time is literally made of discrete ticks, but it does mean that physical change is restricted by minimum scales. The constant also reshaped our understanding of fields. Classical fields vary smoothly through space. Quantum fields fluctuate, even in empty space. These fluctuations are not arbitrary. They are constrained by Planck's constant. Even the vacuum is not truly empty. It seethes with activity governed by quantized limits. This leads to one of the strangest conclusions of modern physics. Nothingness has structure. The vacuum contains energy, fluctuations, and transient particles. These phenomena arise because the universe cannot be perfectly still. Zero action is forbidden. Planck's constant enforces a restless background to reality. Technology offers the most tangible proof of how this tiny number reshaped the world. Lasers operate because electrons jump between quantized energy levels, emitting coherent light. Semiconductors work because electron behavior in solids is governed by quantized bands. Magnetic resonance imaging relies on quantized spin states. None of these would function in a continuous universe. Yet perhaps the most profound reshaping occurred at the level of explanation. Planck's constant